Hi, today I want to express a new dimension of teaching. I would like to simplify the process of the action of bisphosphonate and the role it plays in helping to prevent bone resorption and also to tell you more about bisphosphonate in terms of classroom relationship with clinical application. Why am I doing this? I'm doing this because I was a biochemistry major. I have heard words like POP, pyrophosphate. What is pyrophosphate? Pyrophosphate is one molecule that has phosphate in the center of the building block with O around it. There are about 1, 2, 3 O's at least in pyrophosphate. In one segment of pyrophosphate, then there's one phosphate molecule surrounded by O's is connected to another phosphate molecules by an oxygen molecule. So pyrophosphate is molecules of P's and O's. That's why when you see the short form of pyrophosphate, it's called POP. What does pyrophosphate have to do with what I'm saying? The molecule called bisphosphonate was created from a framework of pyrophosphate. The O in the center that joins the two POPO molecules has been replaced by carbon molecule in bisphosphonate. Hence, it's PCP as opposed to POP. POP, which is the pyrophosphate, is a natural molecule. It's found in many. In fact, it's very easy for an enzyme to digest anything that is carrying POP. For instance, the one popular product that people use, medication, in fact, that people use is called thiamine. Thiamines are available as thiamine pyrophosphate. It's easier for the enzyme to pick it up, and also and thiamine is a cofactor for many biological reactions, enzymatic reactions. Same thing, calcium pyrophosphate. This, whenever all those calcium calmodulin reaction in the skeletal muscles, those are available to the enzymes in form of pyrophosphate. So, why is it important to modify pyrophosphate? There is an enzyme inside of osteoclast, which is the molecule that helps to resorb bone. It chews off bone. And that the name of that enzyme is called farnesyl diphosphate synthase. And farnesyl diphosphate synthase can only pick up pyrophosphate, something that has pyrophosphate attached. So in the absence of pyrophosphate, farnesyl diphosphate synthase cannot function well. So what happens is that if this PCP, this new molecule, that the pyrophosphate that has been modified, enters into osteoclast, it inhibits the osteoclast because the osteoclast cannot use it. So, and it's in the osteoclast, it cannot leave the osteoclast. It takes about 4 hours from the time bisphosphonate enters the stomach for it to get into the osteoclast to inhibit its activities. So that tells us something about the biological activity, how we, the scientists, have helped us modify it, and it takes about 10 years for the bisphosphonate molecule that has entered into bone. This is another area that I would like to talk about. The bone itself is the only molecule that bisphosphonate can go into, because it doesn't stay too long in the bloodstream, is very hydrophilic, and it doesn't go, when it leaves the blood, it cannot enter into many cells, it cannot enter into many molecules, so it's more targeted to the bone because of the structure. So when it goes to the bone, it can mimic the building block of the bone, and so bone keeps building on it. So, and it takes about 10 years for that to get back up. So those are the two ways by which bisphosphonates help in our body in terms of bone structure. So this is amazing. You know, we've been in the biochemistry classes and we've sat all through, and we had 10% of assimilation. But now it's amazing to know that there's a reason why the all these chemicals came up in classes, in tests, and it's amazing to know that there are simple molecules that the scientists have modified, or have been able to modify, and because they know that it is readily available to the enzymes love them, they're able to use it for treatment purposes, because it was like a great breakthrough when bisphosphonate was discovered for the purpose of helping to treat osteoporosis, prevention and treatment of pathologic bone fracture, etc., etc. So kudos to the scientists. What we're looking for, what I'm challenging the scientists to do right now, is to be able to tag such enzymes and create like a roadblock in the bloodstream or around a particular cell, such that when enzymes that work with like HIV virus molecules try to get in, the CD4 cells could be protected. We have done this while we were in college in terms of working on simple cell organisms, and see how we can project that to multicellular organisms like us, you know, messing with the old big structure like human beings. So I think this is possible, and kudos to that. Learning our biochemistry backwards from a clinical perspective of a physician to where we were sitting down and we were very clueless. It's amazing to be able to connect it. So nothing gets lost. We're just clueless at that time. Now we are able to appreciate what our teachers have been doing. All right, thank you.